Welcome to Breadboarding. This is video 53 in the Breadboard 8088 PC series, and this is the 8th part of building a CGA video controller. A high level plan, we first built out an Nanocomp 8088, which is a simple computer using an LED display keypad and a basic monitor. We then extended this to build a basic floppy disk PC with a monochrome display adapter video controller, floppy disk controller, and we're able to boot MS-DOS 330. In this final stage, we're trying to build a PC capable of running early versions of Windows. So we've already built the IDE disk controller and got the computer to boot MS-DOS off the hard disk. This is the last main step in the process to be able to get Windows running. Now, in the previous video, we got the character generator working and the shift register that serialized this. So this was a test pattern that we ended up with at the end of the last video. And what we're going to need to do now is to start add all the attribute and color control, which is probably by far the most complicated part of this project. So this is where we left the project last time with the character generator ROM and the shift register. And now what we're going to need to do is to handle all the video output logic, and we're also going to need to add the CGA control register and the color register, because so much of the logic here depends on values set in those registers. So a lot of the logic we'll be looking at throughout the remainder of this video has really been compressed down into 4 programmable logic devices, which are able to actually compress all of the logic, which probably came from more than 20 odd chips, down into these 4 chips. The rules around here are quite complicated to work out, as you'll see as we go through this video. So CGA control register controls sorts of things about whether blinking is enabled on the text display, controls the text modes and the graphics modes, and then the color register provides various colors, for example, for the backgrounds, overscan areas around the text mode screens, and also provides the foreground color for the 640 by 200 high resolution mode. And as we've done earlier, we've already defined the I/O decoder that we need to actually address all of these registers, so these should be fairly straightforward to wire up. So the information for this has come from 2 sources: the original IBM Colour Graphics monitor adapter hardware reference. So this includes a lot of the tables I'll be referencing as we go through this, and it also included the schematics at the end, which we used in some of the earlier videos. But by far the easiest way to actually consume this information is with the KiCad schematic that I've referenced previously, and I have gone through and annotated this, and there's bits of here which I've now captured and included in these slides, so it makes it a bit easier to see things about the multiplexer here, and you see all the blue comments and things. So I'll make those available on GitHub once I've completed this stage of the project. So that's where the source of this information has come from. What we need to look at first of all is the mode control port and the color register. So the color select register has 6 bits, and there are some inaccuracies in the documentation from IBM. The blue border for 40 by 25 alphanumeric mode, it's for all text mode, so whether it be 40 or 80 column mode, it doesn't make any difference. And also this bit 4, which is known as background intensity, in fact doesn't affect the background alphanumeric mode at all. It's only really the intensity for foreground colors in graphics. So really this would have been better to be graphics intensity, probably would be more accurate. When we're in the 4 color mode, there are 2 color sets that can be enabled. So when the color select bit 5 is set to 1, then we have the background color defined by the first 4 bits here. Then we have cyan, magenta and white, and then if the bit is set to 0, then we have green, red and brown. And the reason for brown is that would be dark yellow, but CGA monitors had the electronics modified to change dark yellow into brown. Then the mode control register over here, there are a number of values here which we use in all of the rules. So the high res one controls whether we're in 40 column mode or 80 column mode. Now originally the CGA used the 40 column mode timing for all the graphics modes as well, but it makes it a lot easier to use the 80 column mode timing. So I'm mainly going to use the 80 column mode timing, then I will try and get the 40 mode working once everything else is working. There's then the graphics bit, so this determines whether in either of the graphics modes or in the text mode. Video enable will When that is set to 1, then we'll get output. If it's set to 0, then it will suppress all output. Then we have another bit there for the 640 by 200 2-color mode. It's not really black and white in that the foreground color for the high res mode is actually determined by these bits here as well. So these bits here can be are used for the various logic controls, and the black and white mode actually allows, on the original CGA card, it would change the composite output to be black and white. Now if this plugged into a CGA Colour monitor, it wouldn't make any difference. What I'm going to do here is I'm going to switch the colour palette to a grayscale one if that bit is set. So this is the sections of the schematic that I've reproduced here. So we've got the colour register here with our overscan intensity red, green, blue, background, which is really graphics and colour select. And we've also got the mode port here with those values that I showed you previously. So graphics mode, blinking, video enable, 80 column or 40 column mode. And then there's another interesting one here. So in order to get some of the range of colours in the 4-colour palette, then select blue is output to enable the blue. If we're in black and white mode and the C0 is enabled, then we get blue. Or if we're in the colour mode and colour select is 1, then we'll get the blue as well. So this is how the blue is turned on and off for the 4-colour graphics mode. And this is just reproducing. The background is in the top 4 bits, the foreground is in the bottom 4 bits, and depending on if blink is enabled, this bit is the intensity. If blink enabled is 0, and if it's 1, that determines if we blink. And as I said, the black and white mode only affects composite output, but we will reproduce that. So this is probably the more important bit of the thing, where most of the complexity of all of the video output is maintained. So the outputs here of red, green, blue and intensity go off to the video output logic and the composite color generation. And we can see here that each of these channels has 4 inputs and 1 output, and which channel is enabled is determined by mux A and mux B. And there's also another STR value here. When this is 0, then all these values are enabled. When this is set to 1, then black comes out of here. And this is only set to 1 in the high-res graphics mode, as you see here. In the 640 by 200 graphics mode, then when it's the background, then that is enabled and we just get blackout. When it's 0, then all the multiplexers are enabled. So we're going to have a look at what the multiplexer A and multiplexer B values are in order to do this. And we've also got here that obviously the medium resolution graphics, the 4-color graphics, that the leftmost bit is determined by bit 6 and 7, with C1 being red and C0 being green. And as we said, the cell blue is worked out on the basis of the logic I showed on the previous diagram. So this is the logic that works out the values for mux A and mux B. And pretty simply, then mux B determines if we're in graphics mode or not. So text mode is 0, graphics mode is 1. And then mux A really is foreground is 0, background is 1. And also then for 1, 1, we get graphics background or the overscan area, or with an exception really, that the foreground color for the high-res 640 by 200 2-color mode is determined when this is set as well. And basically what this logic just does is, when there's a blanking period, when display enable indicates the blanking period, then we get 1 and 1 coming out here, so we get the overscan. When we've got the 2-color mode and there's a value in C0 and C1, then we'll get the foreground. When these are both 0, then you'll actually get the background, graphics background. And in text modes, then when we get dots coming out and graph, inverted graph is true, which means text mode, then again we'll get 0 for the foreground, or you'll get 1 for the background. So really mux A is foreground 0, background 1, and that's further amended that when in the 4-color graphics, then cell blue enables blue for color set 1, and when BW is also enabled. When it's 1, we get the background text or overscan, or in the case of 640 by 200 2-color graphics, we actually get the foreground color. And then mux B really is 0 for text, 1 for graphics, and then the graphics mode we'll use the color register for the overscan for the text mode, the 4-color background for the 4-color mode, and in the 2-color mode it's actually the foreground color is determined by the color register. Then there's another bit of the code which actually determines the character output. This basically takes the character generator dots here, incorporates the cursor output from the CRTC, the cursor clock, the blink clock, the character blink clock, whether blinking is enabled, and the attribute 7, the blinking bit, and it combines all of these to actually say should we show foreground or background coming out of there. This just shows the color set. So color set 0, C1 is red and C0 is green, and you can see those are the combinations. We get brown for what would normally be dark yellow just because the CGA hardware in the monitor was configured to actually output dark yellow as brown. Then when color sets 1, then because it sets blue here, then blue and green gives us cyan, blue and red gives us magenta, and then red, green, blue gives us white. So that's the way how that works. This is a little bit fiddly, we don't really need to worry about it, but it's to do with the way how the high-res black and white mode, 2-color mode outputs, and it's confusing with this bit here just because of the way how the CGA card originally used 2 shift registers, one for C0 and one for C1, but we're not doing that, so we don't need to worry about it. And what this basically does is produces the strobe output as 1 when we want to show the background for the 2-color high-res graphics, and it'll output 0 in all the other combinations. It will also suppress the output of the overscan area during the vertical sync and horizontal sync pulses themselves. So display enable will show when the CRTC is not outputting any active text or graphics, but we don't want to output anything during the vertical sync and horizontal sync pulses themselves. So this logic here really just controls this, and again we don't really need to worry about that too much because we're going to be able to do that a better way. So this is a summary of all of that information really. So we have the control port settings over here. So graph equals 0 is text, graph equals 1 is graphics, high res 0 is 40 column, high res 1 is 80 column. If we have BW set to 1, then it will do a grayscale output, suppresses color. We see here that we've got the foreground colors from the lower 4 bits, the background colors from the top 4 bits if blinking is disabled. If blinking is enabled, then we use attribute 7 for the blink flag, and note that bit 0, the top bit there is 0 and it's not background intensity like the docs mention. When blink enable is 1, then the blink clock will actually force the foreground to the background to cause characters to blink. The cursor output from the CRTC and the cursor clock will actually output the cursor on the raster line row 7, and the overscan area, which is when display enable is 0 and we're not outputting the horizontal sync or vertical sync pulse, we use a color register overscan. And then for the graphics 4-color mode, the medium resolution graphics, then red comes from C1, green from C0, then if color select is 1 or BW is 1, then blue will be 1, otherwise it's 0. The intensity comes from background underscore I, and then if C1 is 0 and C0 is 0, then the background will in fact be the overscan IRGB value. If BW is set to 1, then it will get a 4 grayscale values. Then for the graphics 2-color mode, the high-res mode, then the shift register S dots output, if that's 1, then we show the foreground color from the color register overscan intensity red, green, blue. If the output of the shift register is 0, then we show black because the STR value is 1, which disables the color multiplexer output. So in this we've got graphics equals 1, 640 BW equals 1. And again, BW is slightly confusing because it's 2-color, not BW, in that the foreground color comes from the color register. There's a couple other things need to consider. The video enable is actually implemented in a slightly unusual way. So there's a signal called clear shift register, which is active low, and you can see here in pink that there's a number of latches, shift registers that have the clear signal coming from that. And basically what happens here is if video enable is set to 1, then we will generally get this is set to 1, so output is okay. And there's also a bit here where the display logic around delaying the display enable is then combined with display enable shifted by another character clock. So this basically produces a low pulse at the end of each line. So basically at the end of each line we clear the shift register, or if video enable is 0 then the shift register is cleared. So what this means is until video enable is set to 1 then there won't be any output, and at the end of each line then we'll basically get the various registers will all be cleared. And finally the blink clock. So the blink clocks for the character and for the cursor come from the vertical sync, which is 70 Hertz. So the cursor blink clock is divided by 16 to give us about 4 and a bit Hertz, and then the character blink clock is half of that again at about 2 Hertz. So although the CRTC was able to do the cursor blinking, I don't think it could do the character blinking, and so IBM combined the two in this sort of way. So now let's take a look at the KiCad schematic to see what changes we're going to need to make. So in the last video we added the character generator on and the shift register, and the main thing about the shift register, there is an output S dots, and that S dots is really the foreground background bit that comes out of there. Now the bits we're going to need to hook up here, this is the character latch multiplexer. So this takes the foreground background colours and we'll use the S dots to determine if we're showing the foreground or background colour. We'll also divide up the medium res graphics based on the clock signal QCQB, which goes through 4 cycles every character, and that will actually provide us with the C1 and C0 outputs 4 times per character. That then goes into this PLD here, which combines the various outputs and produces the output to go off to the video digital analog converter up there. This one down here really takes the inputs from the blinking and the character dots, and also will delay some of the vertical sync and the horizontal sync values. So this actually produces an alpha dots comes out of this, which then controls some of the inputs in here as well. This is the color register, and most of these values are just used by this to determine when we need to output the background information, or in the case of the 2 color high-res graphics mode, when we want to output the foreground information. Then we have the blink PLD here. So this takes the vertical sync signals and divides it down for the necessary clocks, and also has the option to invert the horizontal sync and vertical sync, which is needed for some frequency modes require the horizontal sync and vertical sync to actually be inverted. Then we have the mode control register here, which just has our blink enable, video enable, high-res graphics, and high-res 80 column, 40 column. So these are chips we're going to need to wire up. I've already covered the rules in some detail, so I will program the PLDs during the video, but I won't stop during the video to explain all of the rules, in that the rules as I've sort of summarised them is basically what these will be implementing. So this is the region of the board. So what we have is this is the blink PLD down here. This is the mode control port, color register. Then we have the attribute latch multiplexer here, the final output sort of video PLD here, and this is the one that does the text mode, cursor blinking, all that sort of stuff. So we're going to need to hook up all of those. I suspect we've probably run out of time, so what I'm going to do now is to break the video, and then in the next video we will actually just start to actually wire all this up and actually then test it. So if you don't want to miss out on future videos, then please hit subscribe, and if you found it interesting, please hit like. It just helps to make the videos available to more people. Thanks for watching.